Hi there. This video is for the beginning of lesson 2, and you need two things. So one is the lesson 2 notes from the packet from the bookstore, or you may have printed it yourself. That's this one right here. And then there's also a lesson 2 supplement, which is one page or one page front and back, or 2 pages. This is just a reference sheet, so you can look at it online, and I'll bring copies to our next class. But instead of trying to edit this, I decided to make my own version that matches what we're doing a little bit better. So you can replace this whole top portion with this page. Let's go through it and let's do an example. Now, we have done one hypothesis test already around on the study for Parkinson's disease, and then we did a simulation for that one. So now we're going to do all the steps for a theoretical hypothesis test, but the steps are very similar, okay? So it's just a difference in how you find your p-values. Okay, so let's look at theoretical hypothesis test for one proportion. So everything we're doing right now is one proportion. And we're using the idea of the central limit theorem and sampling distribution. So the distribution of all random samples, if the conditions are met, and I have the conditions written for you down here, then we can use a normal distribution. And so that's what we'll be doing. If our conditions are met, we can use the normal model to find our p-value. So here's the steps. Let's go through these. So we're going to write our hypotheses, same as before, null and alternate hypotheses. Then we're going to check the conditions, which we did for confidence intervals. They're the same conditions. Then we're going to write our observed statistic and calculate the test statistic, which in this case is a z-score. That's why it's called a one proportion z-test, because our test statistic is a z-score. And using that, we can find our p-value, and we can also get an image, if needed, of that p-value with the normal distribution. Then we compare the p-value with the significance level and determine whether the result is statistically significant. Okay, remember, small is significant because it's unlikely under the null hypothesis. We're setting up our whole test based on the idea that the null is true. And then we see, well, how likely is it to get our sample statistic if the null is true? And if it's really small, then that's evidence against the null. If it's pretty likely or a big probability, then that's evidence for the null. Okay, so then once we compare our p-value with our significance level, then we put our conclusion in context, include the p-value, whether we reject the null or fail to reject the null. Okay, so those are steps we're going to go through. I've put letters, and I'll start with the letters. You're welcome to keep going with the letters, or you can drop those. It's up to you. Then here are the conditions that we've been using so far in our class. So I've written them out for you so that you have a better set of notes for those conditions. Okay, so I'm going to keep this reference page handy as we go forward, and we'll use that. So I do want to do example 1 here, which is just writing out our hypotheses. It just says practice writing out the hypotheses. 80% of Comcast customers were satisfied with their service. They want to test if they've improved. Okay, so remember that our null is the status quo, or no change. So our null HO is going to be, and we're talking about a proportion, we have a percentage here, p equals 0.8 or 0.80, either one is fine. So the null is the status quo or no change. It's what's kind of already assumed to be true. Okay, so this, or it could be a previous fact. Our alternate is the thing we're trying to show or prove, and they want to test if they have improved. So improved would be greater than, because more people being satisfied would be an improvement. In this case, more is better, but not always. Remember, our null is always equal to a certain value, and then we can have a greater than, less than, or not equal here. Okay, so because this is greater, this is a right tail. This is the, let me write this down first. This is the claim we want to test. And then because it's a greater than, this would be a right tail test. Okay, so I just wanted to write out the hypotheses for that. Now let's go ahead and do a whole example. Okay. On the second page of the notes practice, I'm going to notes packet. I'm going to leave this for optional practice because they use different parameters. So it uses a mean, a standard deviation, and something else. I forget. Oh, I think there's also a proportion. So just going to leave that optional practice. I'll fill it in. You can do it if you want. Right now we're sticking with P, so that's why I'm going to keep it optional. And let's go ahead and do a whole test here. So example 5. Okay, so according to Time magazine, 33% of all cars sold in the US are SUVs. After some investigation, it appears that the actual value is less. Okay, so I'm going to underline that. It seems important. That's a direction, right? Suppose a random sample of 500 recently sold cars shows that 145 are SUVs. Okay, so we also have this 145 out of 500, and we also have our 33%. So that 33% is our P naught, that's our null value, and then these two together are our P hat. P hat is 145 out of 500. That's our sample statistic or observed statistic. Okay, so I'm going to keep my steps handy right here. First thing we're going to do is write the null and alternate hypotheses. So letter A. Our null H naught colon is P is equal to 0.33. And that's called the null value. That's why we write P0 for that, because it goes with H0. So the 0.33 is also called P0. Our alternate is what we're trying to show. We always have the same variable there. And is it greater than or less than or not equal to? They're trying to show, or it appears the actual value is less. So they're trying to see, is there evidence that this has gone down or the value is less than 33%. Okay, so that makes this a left tail test. You don't have to write that, but if it's useful, you can write it. Okay, B, check the conditions to use the central limit theorem, and I'm going to use these conditions down here. Okay, so independence, and I think I may have switched the order here, but the order doesn't matter so much. Let's go independence first. So this is B. Okay, so the cars must be independent, so we're looking at cars sold, right? Recently sold cars. All cars sold is our population. So cars sold have to be independent of each other in terms of the type. Okay, so you might be thinking, well, one car can't affect another car, right? An electric car can't make a gas car electric because they're inanimate objects. But what we want to do is look out for potential sources of bias in our sample, okay? So I'm thinking of SUVs. I'm thinking of, we want to make sure we're not overly sampling more affluent areas, or I don't know, possibly more conservative areas might have more SUVs. I'm just thinking about climate change and cars that use more gas. For example, in Portland, would there be fewer SUVs than Nebraska? I don't know. So these are things we want to be thinking about, right? We want to look for potential sources of bias in our sample. So I want to say something like sample a wide variety of economic levels and political might say political party or also a political leaning. To minimize bias. Okay, so when you're setting up a test, you want to be thinking about all of these things. And then, of course, the second one is randomization. So that is also, those go together because we're taking a random sample, but we want to look out for sampling bias as we're doing that. So 1 and 2 go together. 2, randomization. It does say we have a random sample. And as long as we're looking out for things in independence and not introducing a sampling bias, then we're okay with that. Okay, next one is large population. So this is the one where we need to make sure we are sampling from a large enough population relative to our sample. A population must be 10 to 20 times our sample size. I'm just going to use 10 because it's nice and easy to multiply. Add a 0 on the end. So large population. The population of all car sales must be, and we have a sample size of 500, so 500 times 10, which is 5,000 or more. So I think it's pretty safe to say that between new cars and used cars, it also doesn't specify if this is new or used. But I think either one of those, there's at least 5,000 cars sold in any, I don't know, year or whatever. Okay, last one, success failure. We need to make sure that our NP and NQ are greater than or equal to 10. And remember that because we're setting up our whole test based on the idea that the null is true, we're going to use our null value. We wouldn't use p hat here. We're going to use our null value. Okay, so this is success failure. N times P0. So our sample size, again, is 500. We have 500 cars, so 500 times 0.33. Let's see what that is. That's 165 cars. Great, so that is definitely bigger than 10. And our N times Q0 is 500 times 1 minus 0.33. Now these two will add up to 500 because our two percentages add up to 100%. So there's other ways you could get this, but I'm just going to do 500 parentheses 1 minus 0.33. 335. And we need both of these to be greater than or equal to 10, which they are. 500 is a pretty big sample size, so I wasn't too worried about that. However, if our P was really close to 0 or really close to 1, even 500 might not be big enough. Okay, great. So back on our steps, that's checking our conditions. So now, now we can use a normal model, right? So if all these are satisfied, we can use a normal model. Yay! That's our whole goal with that. Okay, so then C says write the observed statistic. That's our p hat in this case, and calculate our test statistic. Test statistic is a z-score. So let me write the observed statistic first. That's our p hat, which is 145 out of 500, and I want to get a decimal for that. Okay, that's 0.29. Okay, great. So 29%. 29% is less than 33%, right? But we don't know is this just due to just one different sample? Because every different sample we get will be slightly different. Is this just due to normal sampling variation, or is this significantly different? Okay, that's our goal with doing this test. Okay, in order to start to figure that out, we're going to find our test statistic. Now remember, if this is our model, we have a mean and a standard error for all the random samples, and we have just one. So we want to know, where would this random sample fall in this distribution? So to find a z-score, we take our statistic that we have minus the mean and divide by the standard error. So we're going to go ahead and do this calculation. I'll write the formula out here. Z equals p hat minus p0 over the square root of p0 q0 over n. Or you could say p naught q naught over n. Okay, so now let's put in our numbers. We have 0.29 minus 0.33. That's from our null. This is our null value. We're using this in everything. So the 0.33 is going to go everywhere. 0.33, 1 minus 0.33, all over 500. Okay, and now I want to calculate this all at once because I don't want to do the square root and then divide and then round off or have any intermediate round off error. So let's go ahead and plug this in. Let me put it over here. 0.29 minus 0.33. Now we do have a subtraction and a division. So in order to make the calculator do the subtraction first, I either need to put in parentheses around the top, or if you use Desmos, make sure it goes under and it has that whole subtraction on the top line. It's pretty good about doing that. Or what I'm going to do is hit enter, because then it does that calculation. Now when I hit divide, it's automatically going to divide that by the square root. Okay, and my square root button is on top of the square key. These are inverse operations, so they often go together. Second square root, 0.33, parentheses 1 minus 0.33, close parenthesis, divided by 500. And I get negative 1.90217, so 22. So let me write that down. Negative 1.9022. Okay, and like I said, if you're using the Desmos online calculator and you hit divide, it usually will assume you want to divide the whole thing, but just double check. And also make sure that all these numbers are inside your square root, okay? Okay, so this is how many standard errors are we away from the mean or the null value, right? So this is in standard errors. Remember, 2 away is starting to get unusual, but this is really close to 2. So I don't know what the probability is of getting this value, but we're going to figure that out right now. So let's see if I'm still in C. Use the test statistic to find the p-value. So we've got our p-hat. Let me write, just because in this case it's p-hat. We've got our p-hat, we've got our z. Now we're going to find our p-value. And then I'll just draw a little image, but keep an eye on the, I think I said that already, keep an eye on the instructions if it's looking for an image from Staplet. So we're going to use Staplet for this. D, our p-value, this is going to be the probability of getting this z-value or towards the tail. So since we have a left tail test, because also anything smaller than that would also be evidence for the null. So we're going to include that. So anything less than z less than negative 1.9022 equals, okay, so I'm going to go over to Staplet. And yes, here I am. So I'm on the Staplet normal calculator. P-value is an area. It's a probability. And because we're using a z-score, our mean is 0 and our standard deviation, oops, I didn't mean to click that, is 1. So 0, 1 is our standard normal. I can write that down as well. Then we plot the distribution. So just remember, z is distributed as normal 0, 1. So we put in our 0, 1, and we're using Staplet normal calculator. Okay, now calculate the area. Do I want between, left, or right? I want to the left because we have a left tail test, and our z-score is negative 1.9022. Calculate area, and you can show your labels if you want. So you can see here's your z-score, almost 2 standard deviations below the null value or the mean, and the chance of that is 0.0286, so it is pretty small. We're getting down into the tail here. So this probability is our p-value. It's the chance of getting the observed result or smaller or towards the tail if the null hypothesis is true. So if it really is 33%. Okay, so let me write this down. 0.286 is our p-value, 0.0286. Okay, so that's our p-value, which we get from our Staplet normal calculator. And if we were using a simulation, we'd get our p-value from a simulation. Okay, where's my steps? That is D. That is actually part of C. The letters don't matter too much, but I will be consistent because I think that's important. D says compare the p-value with the significance level. Now remember, if we're not given one, we use a default of 0.05. That's kind of our standard, like it goes with the 95% confidence. What's something less than 5%, we consider that unlikely. So for D, I'm going to compare our p-value, 0.0286 is less than 0.05, and this is our alpha or significance level. Okay, so small is significant. We're saying if there are, if 33% of all the cars sold in the US are actually SUVs, then it's pretty unlikely to get a sample with only 145 out of 500 that are SUVs. So this is evidence for the against the null, or for the claim. Okay, so we're going to write that out in our conclusion, but we might just want to say here that this is significant. Okay, in case that helps. So then our last step, E, is stating the conclusion in context. Include the p-value and whether we reject the null or fail to reject the null. Okay, and then remember, in context. So we want to put the what the claim is in there so people reading this would actually understand what the decision was. Okay, let me go back to pink. E, so we could say with the p-value of 0.0286, we reject the null hypothesis. You could also add that it's statistically significant in there as well if you want to. Then I'm going to say, what does that mean in terms of the context? Remember, go back up to our claim. It appears that the actual value is less. So I'm going to say we have evidence that less than 33%. We have evidence that less than 33% of all cars sold in the US are SUVs. Okay, now that is our full test, okay? All the steps. There's one more thing I want to do, and that's a check using our theoretical calculator. So this is a great tool to have. Check using GeoGebra theoretical calculator. Okay, and that is on the second page of that handout. That's the supplement. Really similar to the confidence interval one that I showed you in the last video. So let me go over to GeoGebra, and I'll make sure the link is in D2L. So it's GeoGebra Classic in the probability area, but I'll give you this direct link. And we want to use the statistics tab. Okay, now you'll notice the z-test comes up automatically. Oops, I was already doing this one. Let me hit refresh, see if it'll erase it all. Okay, good. So here's where it comes up on z-test of a mean. So z-test is the default, but it comes up with a mean. So on this arrow, I want to choose z-test of a proportion. And we'll use most of these during our class. Z-test of a proportion. I've got to put in my null so it knows how to calculate this. 0.33. And then left tail is the default, but I would choose right tail or two tail if it was one of those. Just like the confidence interval, we put in our p hat, our observed statistics. I'm going to put in 145 out of 500, and it calculates it automatically. So let's see. We have our p hat, our 145 out of 500, our z-score, which is exactly what we got, negative 1.9022, and our p-value. I wish they said p-value because there's so many p's here. But you can see that p is different from that p. Our p-value is 0.0286. Let me just go back to the notes, and here we can compare these side by side. Here was our z-score, which is negative 1.9022. And then our p-value, this came out exact. Remember I said sometimes these are a little off. This one came out exact, so that's fantastic. Okay, so you can use this as a check, especially if you're getting stuck and you're doing MyOpenMath. Use this as a check, but then, of course, go back and figure out how to calculate that. Okay, great. Well, we'll also do a simulation, but I'm going to save that for another example. Okay, thanks for watching this, and I'll see you in the next video.